So come on to the UConn seminar. We have our speaker, which is Dr. Lemmon from the University of Michael Lemmon, Windows graduate, worked at Stanford University, and after graduating in 1979, he worked for 7 years as a guidance and control engineer on several ballistic missile defense projects. He then returned to the graduate school and completed his PhD degree in electrical and computer engineering from Carnegie Mellon University. After that, Dr. Lemmon joined University of Notre Dame's Department of Electrical Engineering in 1990, where he currently holds the position of Professor in Electrical Engineering. Dr. Lemmon's current research interests revolve around management and control of cyber-physical systems. So, I'm going to talk about a very important topic today. His work has explored the impact that limited communication and computation resources have on the network control system's performance. Most recently, he has begun exploring the resilience of cyber-physical systems to environmental disturbances. And today, we get to give some interesting talk on forecasting regime shifts in natural and man-made infrastructure. With that, welcome Dr. Lemmon.
Thank you very much for the introduction, and thank you for Dr. Pong and the rest of the department for inviting me here to speak. The topic that I'm going to talk about today is a new direction for the work that I've done in the past. It is an emerging issue in network control systems. And the specific issue that we're looking at here are regime shifts, which we'll talk about in a little while. But basically, these are asking the question, why does a large-scale system collapse, or why does a complex system collapse? And how do we forecast that ahead of time? And is there some way to manage that in a constructive fashion? So, probably the first question that we usually have to ask in these things is, why the hell am I doing this? You know, you have to establish the need for the work that you're doing. You can't just sort of say, I want to do this. And so the underlying problem or issues that we're concerned with rely or focus on the fact that humanity relies on many natural and man-made systems for its workings. In particular, it requires that these processes, which we'll refer to as infrastructure processes, provide a consistent and predictable level of goods and services. Because if a disruption occurs to the goods and services that we see, and eventually we see some sort of disruption in society as a result. These disruptions can be minor, i.e., I can't talk to my favorite person on Facebook at this time, or they can be very, very catastrophic in terms of the fact that I don't get to eat or feed my children for the next month or week because I have no power or something of that nature. We basically are looking at a fairly specific set of not just man-made processes, but also natural processes, because we view that these processes, ecosystem processes, also provide this sort of essential set of goods and services. So for instance, when I think in terms of ecological systems, such as the lake system and all of the fauna and flora within it, that system has a fundamental ecosystem function, which is basically to clean the air and clean the water, and to basically provide food and fiber to us. Basically, we have clothes and we can eat and we can breathe in this regard. In addition to this, by man-made infrastructure systems that we're referring to, we're referring to things such as, of course, the power grid, stormwater collection systems, which we had a chance to talk about over lunch, other water, gas distribution systems, all of which basically we require them working well in order to basically have the standard of life that we're accustomed to. As I said before, we view these all as infrastructure systems, not just the man-made ones, but also the natural ones, because essentially they form a foundation upon which our civil society is based and really defensible in this regard. And of course, if we see any disruptions to these particular services that are provided, in many cases they can have catastrophic impacts on public health and welfare. Now, this has always been the case. This isn't something which, gee whiz, we didn't depend on these systems before, and now we do depend on them. The concern isn't so much that we depend on these various natural processes. The concern is that with a variety of external global stressors these days, in terms of, let's say, global economic globalization, in terms of expanded communication and networks, in terms of extended transportation networks, in terms of just the fact that, news that appears on one side of the world can appear instantaneously somewhere else and trigger riots and concerns of that part, as well as, of course, the sort of big thing that we're concerned about, which is perhaps global climate change. And all of these are seen as, or it can be seen that we live in an era of potential global change. And that global change has the ability to disrupt the services that we see. So this is potentially an important thing. Now, I'm not the only guy that says this. If I look at the recent 2014 National Climate Assessment from the federal government, we see a variety of warnings about just the impact that global climate change would have on power delivery, on infrastructure in terms of water infrastructure, which ultimately has an impact on food and on the incidence of waterborne diseases. All of these things we sort of have to worry about now to a greater extent than before. So what it means is that this is a problem which is not just, it's always been there, but it's actually a problem which is perhaps somewhat emergent in nature. And it's important for us to be able to try to address this. So there are many things that I talked about in terms of these global stressors that we have. What I'm going to talk about is one fairly specific change that occurred. And this is what we sometimes refer to as a regime shift. So, what is a regime shift? Regime shift occurs when a system that we're looking at shifts its state trajectory from a nominal operating point to an alternative operating point for an extended period of time. Now, we can also extend this definition beyond the sort of multi-stability issue that we're looking at to a shift in the underlying qualitative behaviors exhibited by this system. So we can talk about this in terms of a change from a convergent stable behavior to a limit cycle or sort of closed limit cycle, or even to a chaotic behavior. So all of these are examples of what we refer to as abrupt regime shifts, where essentially the behavior of the system changes in a very dramatic way from what we saw before. I'm going to try to illustrate this using a very simple example, which comes from the ecosystems community, because the term regime shift is really a term that's used by ecologists. It's not usually used by engineers. So in this particular case, the example we're thinking about is what we refer to as cultural eutrophication of an aquatic ecosystem. Now, cultural eutrophication means essentially that nutrients are enriching the water in the lake, and these nutrients come from man-made sources. So that's where the cultural part comes in. It's our culture impinging upon this sort of ecological system that we're looking at. The problem that we have with this nutrient enrichment is that it can trigger what's called a toxic algae bloom, i.e. the water becomes or goes from this very clear, pristine state, which you see in the left-hand picture, to this very clouded state, where basically the water is unfit to drink. And in certain cases, it actually exudes toxins that can kill you. A very good example of this happened very recently in the beginning of August in the city of Toledo, where Toledo, Ohio had to shut down its entire water supply system as a result of a toxic algae bloom in Lake Erie. Okay? Now, they always have, but because of global warming, because of the increased incidence of cultural eutrophication, this year was particularly bad. So this is a real problem that we're looking at in this case. Well, as we said before, there are many negative impacts to this, which include reduced water quality, fish kills, toxic algae, reduced biodiversity, So what we'd like to do is to use this simple example to illustrate the mechanisms and perhaps ways in which we can predict and forecast the occurrence of these regime shifts, not just in an aquatic ecosystem, but in other systems as well, which may be of more interest to us. So as I said before, regime shift ultimately occurs in response to some disturbance of the system's internal parameters. And we can characterize the types of regime shifts that occur on the basis of the underlying time scale at which these disturbances hit. If I have a fast disturbance which hits in an impulsive nature, then basically we get what's called a shock-induced regime shift. And this basically results because the system state jumps from one equilibrium to another equilibrium in the system. The other time scale that we're concerned about is a disturbance that appears over very long term, which is, let's say, a slow rise, let's say, in a baseline level in the system. I.e., for a power system, this could be the baseline demand that users have for power. In that case, these slow disturbances give rise to what we would call a bifurcation-induced shift. Now, both of these shifts we can see or we can visualize graphically using the aquatic ecosystem model that I just showed you before. In particular, what we can do is we can look at this particular equation, which is a differential equation characterizing the nutrient cycle for phosphorus in the wastewater column. Now, the first term of interest to us is this K of T term, because this really is the external load of nutrient entering the lake as a result of man-made sources that are coming in. We have a baseline load level, and we think of the initial state of the system as being at a low nutrient equilibrium, which is shown here by that little blue dot. And we were to plot the right-hand side of this equation for that particular baseline level K0. We end up with the solid line that we see right there. And what you can see in the solid line is that there are two distinct stable equilibria. One equilibrium is associated with the low nutrient state, which is the desirable state in which the water quality is good. And the other one is associated with a high nutrient state, which is associated with the so-called eutrophic equilibrium, which is basically the cloudy, undesirable one where people get poisoned. So in this, we can see these two mechanisms that we're talking about. If I look along the x-axis, which is the state space, an impulsive shock that hits the system is going to result in a jump in the system state. Okay? And that jump in the system state, if it jumps the system state to the alternative equilibrium's region of attraction, means that that system state will stay there, altering, of course, any future disturbances. This is what we refer to as the shock-induced equilibrium, because it's induced by a shock hitting the system in this case. The other one, which is the bifurcation case, occurs when I have, let's say, a step function change to that baseline level, which is shown here on the y-axis, where now we see that K0 is added onto by this sort of high, this steady state function U of t in this case. This represents a long-term variation in the parameters of the system. And if we have the jump that occurs, that helps. I don't have to just do that.
And the interesting point, the one here.
Oh, okay, thank you very much. So basically what we see then is that the solid line, in this case, shifts up. And of course, the important thing to notice here with the shift up that occurs is that the low nutrient equilibrium vanishes in this case. Whereas the high one actually remains, or it shifts over somewhat. And of course, what that means is that even if we were stuck here at the low nutrient state before this shift occurred, after the shift occurred, because this is the only remaining equilibrium, the system state is going to move. So this is what we would refer to as a bifurcation-induced shift, because it's induced by a bifurcation in the underlying system itself. In this case. So there are two mechanisms, which are basically separated in terms of the underlying time scale. These mechanisms occur in other systems as well. In fact, they occur in just about any system where there's some sort of congestion phenomenon where we're hitting up against the limits of the underlying physical system we're looking at. You can also see this in a power system. So for instance, if I consider a classical two-bus system, and this is pulled out of a textbook in power systems, so this is trivial stuff. And if I were to, for these particular load parameters, if I were to plot the power leaving the load bus, which is bus 2 at this point, as a function of the real voltage and the imaginary voltage on that load bus, then we would see that there are actually two equilibria that we need to work with. One of these equilibria, if we have a shock occurs, may shift us to the low voltage. Basically, we lose that temporarily. And the other one, of course, can occur if we change the parameters on the load in such a way that the high or the nominal voltage equilibrium vanishes, which is what we usually refer to as a voltage collapse. But again, both mechanisms should be here, both a shock-induced as well as a bifurcation. So, our problem here is to examine both of these particular mechanisms and to basically find a way of forecasting or predicting them. And to do that, we need to move away from this sort of fuzzy heuristic model that I gave you for regime shift and talk about a fairly concrete mathematical explanation. So, let's first start with the shock-induced shift. The way that we view this is as what's sometimes called a first passage time problem. What we really want to do is we want to bound the likelihood that essentially a sequence of shocks that are hitting the system are basically going to force it into the alternative equilibrium's region of attraction. So for instance, in this picture where we show the state space for a two-state system, and we have nominal equilibrium here in the alternative region of attraction in the shaded region here, a sequence of shocks resulting in a jump in the state space and then a subsequent relaxation in between the shocks. And if these shocks hit in a fast enough progression, then there is some chance that we're going to get the state all the way through in this case, in which case we exhibit this regime shift or the shock-induced shift. So we model this as a jump stochastic differential equation in which the process, or the noise process that's driving this, is a shock noise process whose impulses arrive at Poisson times and whose magnitude basically satisfies some underlying probability distribution. And then basically we say that if the initial state we know to be at the nominal equilibrium, and then we let x sub t denote the region of attraction of the alternative, then that first passage time is the very first time when a trajectory starting at x0 crosses the finish line, so to speak, or into the other region. Now, in general, because of the random disturbance that we have here, it means that that time is a random variable. And so what we want to do here is really characterize the probability distribution of that first passage time. And we use then that as a measure of how likely this type of shift is to occur in the environment which is characterized by the shock noise process, which we've identified. So this is the problem that we can use to characterize the shock-induced shift. For the bifurcation-induced shift, we have to come up also with a problem. And so in this case, what we want to do is we want to determine the range of parameters about a nominal parameter that's been given to us, for which a system x dot equal f of xk, where x is the state variable and k is the parameter space, does not have a bifurcation. So in other words, we're looking for a stability region or a region of parameters for this nonlinear system in which we can guarantee this shift in structure doesn't occur. So formally, this notion of a bifurcation is defined as follows. If we consider a parameter k, we say that this is topologically equivalent to the nominal parameter k0 if the flows, and by the flows we mean this sort of map of trajectories in the very neighborhood of the equilibrium, if that structure does not change in a discontinuous fashion, as essentially we move to the other. And it's that discontinuous thing that we're worried about because that represents a shift or a jump in the structure of the underlying system. So the bifurcation then occurs for systems that are not topologically equivalent to the nominal system. And if we were to identify in the parameter space, which is what we show here, all of those parameters which are bifurcations from the original K0, we end up with that set of parameters which are outside the shaded region. The minimum distance to bifurcation, which really identifies the smallest size perturbation and parameter we can accept before the system shifts its structure, is to basically find the distance along that bifurcation manifold, or find a point along that bifurcation manifold, which is closest to K0 in some sense that we are free to define. And so that's an optimization problem, where basically we need to search for this point. We refer to this as the distance to bifurcation problem, or the D2B problem. What we want to do here today is basically use a common framework to solve both of these problems. And this is the main thing, is that while these look like they're two different things, in reality, the underlying tools that we can use to solve them should actually be the same. So that's what we're going to talk about. I'll talk about it in a second. The benefits of this proposed approach from the empirical work that we've looked at so far are, first of all, that these bounds that we obtained here basically provide a guarantee for which we know that no regime shift should occur. So that they actually provide some guarantees on future performance. Moreover, using the techniques that I'll talk about in a little while, the bounds appear to be tighter than what we can usually obtain using other methods. And moreover, the last one, which is fairly important, is that the analysis that we use to get these bounds is something that we do computationally. And that means that we can build tools. And we can take those tools and take them to the practitioners, the application engineers, who really care how robust or how sensitive their systems are, and let them use them in a way that allows them to manage their systems in a way which they never really thought was possible. Now, we don't get this for free. Nothing's for free, right? So what do we have to give up? In exchange for these benefits, we need to realize the process as a polynomial system. When we have such a polynomial realization, then it means that we can use, it's not really a new method, but it has gained a lot of popularity recently, the so-called barrier certificate methods, as well as concepts from algebraic geometry, to recast both of these FPT and D2B problems in the same framework. And that framework is that of a polynomial optimization problem. Now, polynomial optimization problems are hard to solve in general. But in recent years, there have been ways of developing approximations to them in which we relax the original polynomial optimization using either a semi-definite program or a linear program. And then we solve a sequence of these relaxations in which the order of the relaxation gets larger and larger. And hopefully, as the order gets larger, the approximation to the real solution gets bigger. And that's the basic idea. And we can do that in both of these cases. So let me say a few things about polynomial realizations. Do we have a clock somewhere? I have like no idea how long we're talking. So, so give me like a 10-minute warning that or a hook or something that I'll make sure. So the first thing I want to say basically is that when I talk about polynomial realization, remember this was the price we paid for doing this. Polynomial realization doesn't mean the system is polynomial. What it means is that if I take the original system in which the f, i.e. the right-hand side, is some smooth vector field which is not necessarily polynomial in nature, I can find a nonlinear state space transformation such that for the new state space variable x that I defined here, that function, that system will have polynomial, will be polynomial. So it means that we can take the system and we can transform it through a nonlinear similarity transformation. And for those of you who are in control, You already do this to some extent in your nonlinear control class. And, of course, you do this in your linear systems theory class. There's a whole chapter on realization theory. So this is just a nonlinear version of that in this regard. So, there are many cases where we can actually do this. How restricted is this assumption? Well, a lot of people studied this back in the 1980s. They studied this basically when something known as essentially Volterra series were very, very hot at that time in nonlinear analysis methodologies. They're not so hot now, but they were hot once. And a lot of people wrote papers on this, but also specifically what you'll find is that there were a variety of necessary and sufficient conditions established which basically told you when you could do this. Now, the primary result that I'm familiar with is this one that appeared in 1988. And what it did is it took advantage of the fact that polynomials have a very rigid algebraic structure because they form a ring. And that ring algebra, so to speak, that you're dealing with, basically means you can take that and obtain algebraic characterizations of observability. It's those algebraic characterizations of observability which form the basis of these necessary and sufficient conditions. But the more important thing is that the proof that this guy gave us was constructive in nature. Basically, he said, this is sort of how we go about doing that. And the basic idea involved in all of that was to find, I'll just use, for lack of a better word, a clever variable substitution, where you look at some specific smaller part of that non-polynomial system and say, well, we'll just treat this as a polynomial variable, and then see if you can do it. Of course, you can't do this all the time, but hell, even if you can't do it over a compact domain, I can usually approximate anything closer to a polynomial. So it isn't that large of a restriction. We'll show you a couple of examples. Here's the polynomial realization for the two-bus system that I gave you before. What you see on the right-hand side are basically the swing equations and a voltage control equation, which is on bus 2. The usual sort of Drew control mechanism, as well as power balance relationships for the real power at bus 1, bus 2, and of course the reactive power in this case. And what we do is we introduce, well, we notice that, well, if I put PE1 and PE2 in these two differential equations, of course this is not polynomial because I have the cosine and sine terms there. So what do? I just rename them. In this case, if I rename them, I get these equations, and if you inspect this, this is polynomial. So even your power system is going to look like this. Of course, our original interest, and the people I was originally working with, were all ecologists. So we looked at some of their systems. So this is basically a 3-level food web consisting of producers, algae, primary consumer, which is sometimes called water flea, it's a little bug, and then of course a big fish is a secondary consumer. A differential equation which was developed to model this by the ecologists back in the 1990s is given right here. The important thing to notice here is that the response function associated with the algae is nonlinear in nature, it's a rational function. And this is because most of these response functions have a sigmoidal nature, and you can sort of approximate them in that fashion. So again, I need to transform this into a polynomial realization. What I do is I introduce a new variable, x4. It basically represents 1 over x2 plus k2 plus x1, and this transforms very easily. For those of you who have a background in chemical reaction networks, you'll also notice that this sort of thing also has what we sometimes refer to as Michaelis-Menten reaction kinetics for reaction network, and X4 here actually corresponds to an enzyme in that case. So they're the same, but one is very good for us to work with. So hopefully I convinced you that the polynomial realization is not that great a restriction in this case. So let's go on to the real meat of the matter.
So on what condition you can find such a transformation?
The condition that I remember seeing basically says that you construct something known as an observability algebra. And so if you think in terms of the underlying sets that are reached, okay, or defined there. You can define it, essentially it's not a sigma algebra, it's an algebra of sets associated. And so basically that algebra being contained in a finitely generated algebra works. And because the algebra is finitely generated, that's the polynomial that comes in.
So when you look at the problem, can you see whether you can find a transformation?
I can't tell. I'll be quite honest. What we were concerned with first as we did this, we looked at, oh gee whiz, these work. And then we said, well, how general is this? Do we have existing results? And these are the existing results we have. The thing I think that's valuable is that, at least in terms of the algorithm or the construction that we saw for the proof in 1988, that it does give you hints on how to. And as you can imagine, what it really is trying to do is it's trying to identify those sub-functions within the original system from which that algebraic structure is in some sense. I'm not a great algebraist, and I won't presume. I'm just an engineer, guys. So, a well-read engineer. I'm an engineer, nonetheless.
Your system is switching activities, switching operations. It seems the knowledge of there are different equations. How do they split that?
So in this case, there are a couple of ways of doing it. It depends on how it happens. If it happens in such a way that the underlying curve itself has a behavior which is still continuous, but maybe not differential at one point, and you probably could approximate that with a polynomial system. But even if you can't, you can introduce what's sometimes referred to as a piecewise polynomial approximation, which you can take as a generalization of piecewise affine systems. Some people have looked at this, but it has not been well studied in the hybrid systems community because it's so much easier to work with affine systems. But some people have. So I have a good friend that I'm building who does this, and he does this. But it is not that well studied. In fact, that's the potential open solution. Any other? No? So I want to talk about the earlier certificates because this really is part of the interesting part of this. And I'm going to check my notes because I have a tendency to get off track from I might miss something every now and then. So is there anything I might Okay, yeah, that was the one. So what's a certificate? A certificate is basically seen as a generalization of a Lyapunov function or a storage function, something which all of us in nonlinear analysis have used frequently in the past. But the way we use them here is we use them as a tool for verification. We use them basically to verify whether or not a system has a property of importance to us, like stability, reachability, or safety. And in the past literature, this is primarily the way that you've seen it used. The basic idea for this is we introduce a set of test sets. And that test set, whether if it's empty, in other words, we define it in semi-algebraic fashion. If we can guarantee that that set basically doesn't exist, then this actually can be taken as verifying the property of interest. So the hard part is finding a way to test the emptiness of the set. And for this, we have a very famous result from algebraic geometry, which for lack of a better term, since I don't speak German, we'll call the PSAPS theorem. The PSAPS theorem says that if I have this semi-algebraic set, so this is my test set right here, defined, and what makes it semi-algebraic, remember, is that it's defined by polynomial inequalities and equalities. So if I have this set, omega, x, and Rn, defined such that fi of x is greater than 0, for I equal 1 to n, gj of k is equal, or x I should say, sorry, that's the title, is equal to 0 for all for j over a range. So these are the set of inequality constraints I have. Then this set is empty if and only if I can find a polynomial f that lies in the cone generated by this set of s of i's and another polynomial g in the ideal generated by these g's of j's, such that f plus g plus 1 equals 0. So you're going, oh, what's the cone and what's the ideal? Big fancy term. For us, it means simply, if you think in terms of linear spaces, remember, we're doing things in a more general algebra. So essentially, for us, these are rings and things like this. But ultimately, the ideal is like a subspace. And basically, to say that it's spanned, or it's generated by the G sub j's here, simply means we take linear combinations of these particular elements. The same thing, to some extent, can be said about Jacobi. So what this means is that when I look at this, what I'm really looking for are the coefficients that multiply the f sub i's and the g sub j's such that this is true. It looks very much syntactically like a linear feasibility problem, a linear programming feasibility problem. And that's something we sort of know how to solve in this case. So we can find this using this as part of a linear feasibility programming problem, and if that exists, then we know that this set is empty. So this existence of this function is what we call a certificate, because it certifies that the set is empty, and thereby certifies that the property we're interested in holds. Okay? So, an easy way to illustrate this is with something like stability. We all know stability at this point. In this case, the property of interest is the equilibrium is asymptotically stable, but with a specified rate of convergence slower than a number beta. I'm not going to tell you what I mean by convergence slower. I'm going to be a little fuzzy about that, but I think you'll see in a second. So this property has a Lyapunov characterization in which we seek a certificate function, a Lyapunov function, such that v of x is positive, and such that v dot is less than minus beta, the usual stuff. So if I can find that v, it means a set is empty, and if a certificate is found, then the convergence rate must actually be slower than beta. So we can now use this as a test for that property, and we can apply this as sort of an oracle machine. Now, oracles are things that we see in computational methods. Basically what it says, and you've used them many times. I think a number of you have probably taken a robust stability course, right? And if you've studied robust stability, you compute the H infinity norm of a transfer function using something called a bisection. Well, I see lots of blanks here, so I'm not going to talk about it. Okay. So the point is that an oracle, of course, is this magic person who tells you whether you're on this side of the line or that side. Okay? So for us, the PSAT system is an oracle. It tells us the convergence rate is on this side of the line or that side of the line, where the line is defined by beta. What this means is that if the oracle can tell me that, then I can propose a different beta, knowing which side of the line I have to be on. And then I can apply the test for more time, and apply the test again and again and again. And if I do it in that fashion, not only do I get this property, but I can actually identify a bound on the actual rate of convergence with respect to this underlying Lyapunov function. So not only do I verify the property, but in some sense I can optimize it. Okay? And that's sort of the key to the use of these methods in this case.
So those PIs are those scalar functions?
In this case, they're scalar functions. That's why we have many of them. So essentially, they're all scalar polynomials. And f sub I are all polynomials in this case. So, we're going to do this for shock-induced regime shifts and for the distance to bifurcation problem. And for the, I'm going to start with the shock-induced regime shift. And for this, of course, we need to identify the property that we're looking at. The property is sometimes called stochastic reachability. And what this says is that the system properties at the state trajectory starting at the nominal equilibrium leaves the nominal region of attraction within a specific deadline with a probability that is less than 1 over gamma. Okay? And I can state it in this fashion. And the randomness, of course, comes from the fact that the underlying dynamical process we're studying is a stochastic process. In this case, a just stochastic process. So the certificate that verifies this property is a polynomial function which basically is 0 at the nominal equilibrium, is less than gamma, and such that LV is less than 0, where L is what's sometimes called the generator of that stochastic differential equation. Now remember, for us, the generator looks like a Lie derivative, but at an additional term which corresponds to the random walk associated with noise that goes through. Okay? And for Brownian motion, that's a pretty standard sort of square term. For the jump process that we're looking at, it has an integral term, which is a little bit more difficult to get. The point is that if I have this property enforced, and what I know is that I put the system state through that function v, and essentially it means that this process, vx of t, is a supermartingale. And the supermartingale is a very special type of Markov process, which I always get it backwards. It's either always increasing in terms of the expected value or always decreasing in terms of the expected value. In terms of the gambler's dilemma, it's either the house wins or I lose. Or the house loses, sorry, one of the two. And so the point that I'm saying here is that for that super martingale, we can actually characterize the probability that v of x is greater than gamma. This actually characterizes leaving the region of attraction of interest. And so this actually gives us that probability that we were interested in this case. So if we can find that v, you get this down. And of course, that's exactly what's done in this case. In reality, these problems are usually solved using, and I'll say a little bit about this later, using so-called sum of squares polynomials to form a basis for the function v that we're interested in. And in recent years, there have been some really nice tools that have come out basically providing MATLAB interface to the semi-definite programming routines so that anybody can do this. I mean, it's like LMIs used to be like 20 years ago. And so that's we can solve it. That's the solution. Or that's the problem we have to see. There are some improvements that we made to the original thing that I showed you there. That particular approach that I discussed for stochastic reachability was developed by Prajna, the Caltech guy working with work that Pablo Carrillo had done back in 2000. And in that particular thing, they assumed originally Brownian motions. We extended this to jump processes so that this actually works for the shocks that we're dealing with. The other thing we did was we also modified the super martingale condition, so it actually is quite a bit tighter than the original one that was used by Prajna, which is an easy one. In this case, it requires minus alpha v of x beta of t, which is a function of time, basically the horizon that we're looking at. And in this case, we can actually go ahead and compute the entire probability distribution for a specific problem of interest here. So in this plot, what you look at with the circle and the dashed line, these are the results characterizing the first passage time using a Monte Carlo simulation. So you can think of this as the truth, so to speak. The blue sort of dashed one is what would have been computed if we used the LV less than 0 condition, which is Prajna's original result in this case. And the black one is what we compute using new methods that we have. The first thing you can say is it's tight. It actually captures where the inflection really occurs when we start getting some, we go from basically 0 to something. And it actually does a better job of capturing when we start losing the probability goes to 1. So we can do this, we can do this better, nothing earth shattering to do. You can also do this, as I said before, for the distance to bifurcation problem that I talked about earlier. And this is a problem that's been well studied in the power literature, because back in the 1990s, I believe it was, Ian Dawson and a bunch of others began working on this. In that early work, the method that was used to solve this was sometimes referred to as numerical continuation. And basically what they would do there is they would start from the initial parameter, or the baseline parameter, which would be K0 here, find a point on the bifurcation manifold, and just search the bifurcation manifolds in numerical fashion. Now the problem that you have with that, first of all, is that that search is local, and that means ultimately that the solution you get is only going to be a local equilibrium. So that means ultimately it's only an upper bound on the actual distance to bifurcation. And that means there can be many times when essentially your distance to bifurcation is not yet at that minimum that you identify using these methods, and yet your system collapses. Because basically you didn't really capture the lower end in this case. Another issue that we have here is that the computational complexity of most continuation software limits us to 2 or 3 parameters at a time, and for some, especially for ecological systems, this is too small. So we can close this using certificates as well. And as far as I know, there's only been one other group in Germany that's discussed using this, though not using the semi-definite programming relaxation solution. The certificate,
Why computation is so slow?
basically, there's a big difference between what we do and what they do. So first of all, it requires that you have a surface that you're looking at, which may not always be the case. You may not be an n-1-dimensional manifold that you're looking at. And then what you do is you actually find it and then you numerically compute and recompute each equilibrium point. And that just takes space. It takes space. So in the MATLAB tools that we looked at was the SnapCon, and there's another one I believe that we used. They all basically broke down. It really depends on the nature of the problem. For these methods we're using here, it does still break down to just too big. I mean, nothing is.
What, 4 or 5?
We've been able to run it up to 8 to 9, and we actually think we can probably run it to 12 in this case. Again, it's a question of being able to run tools, which are available to do this. And the solution method is a little different. In this case, all of that computation is really done numerically. But in our case, and in this case, most of that computation is done symbolically. And so there's a very big difference in terms of what
Well, to do what?
Yes, these are done offline. These are done offline. Without a So, okay, as I said before, we have to identify the test set. We have the property. And so the test set consists of those parameters which are not topologically equivalent to K0, points out here, and those that are within the distance beta of K0, i.e. within this sort of ellipse line. And so the intersection is really the test set that we're testing the mutants for. If we can verify or find the V, then basically we know that this test set is empty. And essentially it means that we know that the distance to bifurcation must be greater than that beta which we identify, or V inverse beta in this case. And that we know in that case. So it's not an upper bound, it's a lower bound. And so what's useful here is it provides a guarantee on that system stability, which you really didn't have. Okay.
How efficient are your oracles?
Efficient in what way?
How fast?
This is under work, and so it can vary again, and I'll talk about it. Because that's a very important aspect of these particular methods. So, again, you can solve these using sum of squares relaxations, as we talked about before. And this goes back to Dr. Wu's question about the efficiency. Sum of squares methods have been very well used by a number of people to solve these problems. They're sort of like a hot golden item in the control systems community. But what many people have found is that as the order of the system increases, the computational complexity associated with solving that sum of squares program grows. And ultimately that's because the current state of the semi-definite programming solvers we have is not very good. Semi-definite programming is something that looks like a linear feasibility problem. And remember what I said before is that basically from that PSAT theorem, we're looking for a certificate which to some extent is like a linear programming feasibility problem. But in reality, it's sort of deceptive. It is a syntactical similarity. Syntactically, they look the same in terms of the language. But in terms of the actual objects that we're optimizing over, they're not the same. And so what this means is that for the STP solvers, we lack one really important property that's used in linear programming, and this is strong duality. And it means we have a really hard time developing good primal border. So there's a limitation. Limitations that we found here are up to maybe 7, 8 parameters in this case. But there are ways around that, and I'll mention it. And that's how we're going to do it. There also is another issue besides the solving of this as well, and that is we have to actually get these semi-algebraic conditions. And for this particular case, where we're looking at a saddle node bifurcation, these conditions that we're looking at are conditions on the characteristic polynomial of the Jacobian matrix as a function of the parameters k. In other words, we don't use a number vector that's a real number. We use a function to characterize that constraint. And getting that function has a complexity that's associated. There too, they're not trivial problems. But in return for it, so here's the voltage collapse. We can also do the same thing for fluid webs, and what we see here is that we get a much tighter lower bound on the distance to bifurcation. This was computed using our method. We get a sensitivity of 0.032, and in this case, if we used an existing sort of continuation method, we've got a very loose upper bound in this case. The greater sensitivity we find here for our methods, and this actually is the value of using this, is that we can simultaneously test many parameters at once, variations in many at once, whereas the other method can only do 1, 2, 3 at a time. And it's the same sort of thing that you see in traditional stability analysis, or robust stability, where you say, the gain margin could be the gain margin or the phase margin, or it could be a more complex thing in which you look at the correlated change in gain and phase. That leads to robustness. So that's why this is better from that standpoint. You can deal with more, but of course, nothing's for free, right? And that's the important thing. So, I'm probably almost done, right? Okay, so I'm almost done here. So some tricks of the trade. So this basically are the computational issues that doctors have alluded to before. And the first one I said, remember, we have to actually compute the bifurcation condition as a function of the parameter k. And ultimately, that means we have to solve for the equilibrium of the system as a function of k, parameters of interest. So this means we have to compute a solution to a polynomial system in which the answer isn't numbered, but is a function of k. In this case, because things are rational, polynomials are rational functions. So the basic trick for doing this is to basically compute what's called a Grosvenor basis for the ideal, i.e. a range linear subspace, generated by the polynomials in fx given k. And think of that as a basis. A very nice basis, which is easy to sort of solve in a backstepping fashion. It's sort of like what we do with linear systems of equations when we triangularize them, bring them to row echelon form, and then do back substitution. That's basically what the Grosvenor basis allows us to do, but for a range. A different algebraic structure, but it's, it's the same fundamental. The problem is that the existing algorithm for computing a Grosvenor basis is doubly exponential with the number of variables. That's like impossible to solve. That's really bad in this case, right? So there's a trick, and this trick was basically discovered by the biochemists back in around 2005 in Magdeburg in Germany. And this is basically to take the original system, so equal f of x given k, and project it up to a higher dimensional space where the underlying polynomials are binomials. And for binomials, it turns out there's some very efficient Grosvenor basis algorithms that are an order of magnitude faster. And there are codes that we can use. So there are tricks that we can use. The second one that we say here is with regard to the polynomial optimization. As I said before, polynomial optimization is hard to solve with NP holding back. But what we can do is we can approximate. And the approximation, in general, using the SOS tools, is done basically using the sum of squared polynomials. But as we said before, these solvers are somewhat limited. And what it means is that there are actual limitations to the size of the problem we can usually consider. But we don't have to. Remember what I said before is that f plus g plus 1 equals 0 problem is basically a linear feasibility problem. So if we use something other than sum of squares polynomials, maybe we can recover the linear programming instructions. And that, in fact, can be done. We use a separate set of, a different set of polynomials, what are sometimes referred to as Bernstein polynomials or Handelman polynomials. And then for that case, this sequence of relaxations we use actually do become linear programs. Now, linear programs scale to tens of thousands of areas, easily. And this is a consequence of these great revolutionary results that took place in like the mid-1980s. The thing that AT&T and Marvell didn't want to share with the rest of the world, and all the optimization people really recognized at that point in time. And so you can do this, but again, nothing is for free. The reason why people like the sum of squares and the SDP relaxations is that it was proven by a very nice guy up in France, at Lasserre, that as you increase the order of that polynomial representation, your relaxed solution gets closer and closer and asymptotically converges to the solution of the original polynomial problem. That doesn't necessarily happen in the OP. You get closer and closer and closer, but at some point you sort of stall. Well, but again, you can compute it. So the question is, where is the trade-off? That's actually what we're studying right now. We're trying to do and figure out exactly how far we can take these methods and use them, where the actual limitations can be in this case. So I hope I didn't bore you too much. Benefits of the approach, as I said, this is sort of a model-based approach to regime shift forecasting, in which we assume the process is polynomial. We use certificates to recast the problem as a polynomial optimization problem. The advantages of here are basically tighter bounds because we can deal with more parameters simultaneously. We get a lower bound on the stability margins that we have here, which appear to be very tight. And we have computational tools that we can put in the hands of those that are not mathematically sophisticated. There are also a number of future research directions that we're looking at this time. And since I'm out of time, I'm not going to go into this. I would be happy to discuss them. Thank you for listening.
So going back to your original motivation.
Here, we can take this back.
So your study, what does your study reveal? What's inside? So the current power systems or current power systems?
Well, basically, what it does, I believe, is it gives us the type of way of characterizing the likelihood that these systems will collapse. And so, we'll have ecological systems or power systems. At least in power systems, we suspect they should be able to develop better local indices for stability and current there. Ecological systems, it's still somewhat open because the models at the ecology side are pretty fuzzy. You know, it's very hard to validate. And yet, there may still be, that's actually what we're looking for. But what it does, we believe, is provide a model-based method for forecasting the likelihood of shift. And because it is a model-based method, it means that probability of shift can be related back to real things that I can control. So we believe it forms the basis for policy. And ultimately, that's what we do.
For LP, you are using sharepoint methods?
Of course. I mean, for this, you have to use it. To be quite honest, I don't even think anybody uses anything else. Even when I look at, if I look at MATLAB and I look at the solver, past a certain size, it always defaults to interior point methodology.
I'm not sure what's simplex.
I know simplex can be very good for the right size problem, but I remember reading in that book that they actually do default now to IP type, the final pool. And so they're fast. So, I mean, from our standpoint, if we get it to an LP problem, then essentially we're not worried about the computational complexity of, either run out of space. But we do worry about the fact that the number of basis polynomials that you might need might be very, very large, in which case the benefits of the LP are sort of outweighed. And you don't know those until you look at specific examples in plain. So right now, to sort of test that out, we are looking at a signal cascade called the MAPK cascade. It's a very famous one that some type looked at. It appears all over the place. And it's interesting because you can scale it up very easily. And so we're using that to study scalability issues. But we don't have it with the advanced stuff. I think it is better. We'll see.